Okay, so we are in this session, we're going to go over some of the basics of linear systems before transforms. This is a fairly small group, so feel free to ask questions, or if there's topics that you would like covered that we haven't covered, I'll either try to do today or we can pick it up next week's session. So here are the learning objectives for today. We're going to go over what an impulse response is, and hopefully you'll understand what it is and why it's useful. We'll go over how to expand the signal in terms of weighted and shifted delta functions. We will describe and apply the definition of a linear system. We'll have some exercises on that, just to make sure you're up to speed on that. We'll go over the superposition principle, and then we'll talk about shift invariance. And then we'll talk about how convolution is used for linear shift invariant systems and the sort of critical role of the impulse response. And we'll talk a little bit about how to compute the convolution of an arbitrary function with a shifted delta function, which is going to be incredibly useful for the remainder of this course, and a little bit about the convolution of two direct functions. So this is not really a whole course on linear systems, so we're not going to go into convolution in too much detail today. The idea is just to give you enough that you feel comfortable with working on homework problems and other things that may come up in this course. So first of all, just to review what we mean by an impulse response. Professor McVeigh has already touched upon this in some of the lectures. And the idea is the impulse response is the response of any system to an input that you can imagine is sort of very, very small input. So like if you put in, if you were to image a pin, a very small dot, and let's say this was the dot you're trying to image, then the response would be a blurred image, and that would be the impulse response. And the reason why impulse response is very useful is because we're going to see that any input can be thought of as a weighted sum of impulses. And so if we know the sum to one impulse, we're going to be able to figure out the response to any arbitrary input by just treating that input as the sum of many, many impulse responses. So we'll get into that in a little more detail, but I just wanted to give you the overview of where we're going with this session. So these are some examples of what you might do in to characterize an impulse response. So for example, here you might have a very thin wire, and you might want to see what the impulse response of a very thin wire is. And in this case, that wire, when you image it, becomes a blur. In this case, it looks like a Gaussian blur. And so that would be the impulse response of that. In here, it's called PSF. So another term for it is point spread function. Okay, so you see the term PSF, that's the same as impulse response. It's essentially the response to a point image or point target. Okay, so the notation that we use in engineering and science for an impulse response is we describe things as delta functions. And in this case, we're using continuous delta functions. And so we can have a 1D delta function here. So we'll talk a little bit about what that means in a minute. And then we can also have 2D Dirac delta functions, which are a function of x and y. Sometimes people have put this little 2 in front, but in this class, I think we'll just sort of use that notation. So if a delta function depends on 2 variables, then it's a 2D Dirac delta function. Obviously, if it depends on 3 variables, it'd be a 3D Dirac delta function. And you can also have n-dimensional Dirac delta functions. In this class, we'll stick with 1D and 2D Dirac delta functions for the most part. So just to take another look at impulse responses. So we will denote the input to our system as a Dirac delta function. And we typically use the letter H, although any letter can be used, but for this, most of this lecture, I'll use H. And so H of X would be the response of the system to an impulse response. Okay, the Dirac, in this case, specifically, mathematically, we're going to use the delta function. And then in a practical system, such as the X-ray system that you've been looking at with Professor McVeigh, then in practice, we might put in a point object into our system, and the image, the X-ray image of that point object is then the impulse response. So in general, we want to know what the response of a system is to any arbitrary input f of x. Okay, so in this case, we put in f of x, we put into our system, which is characterized by our impulse response, and we get g of x. Okay, and if this system has certain properties, in fact, if it's what's called linear shift invariant, then the nice thing is we can write g of x as f of x convolved with h of x. Okay, so we're going to go over that in the next hour or so, and so you get a feeling for that and why and how to sort of think about that and get more comfortable with that. But this is basically what we're working up to. That the reason the impulse response is so important is because given any input f of x, I can tell you the output g of x simply by convolving it with my impulse response. Okay. So what that means is if I had an arbitrary object for an X-ray system, as long as I knew what the impulse response was of my X-ray system, then I could tell you what the image is of the X-ray, or the image of the object is through the X-ray system. Okay, so we're going to shift gears a little bit. So that's what we have to say. So that was, we've covered impulse responses a little bit. We've talked about delta functions. The next thing I want to do is shift gears a little bit and talk about how we represent signals and images. And so there's really, the main distinction we're going to make is there's things that are discrete and there's signals and images that are continuous. Okay. So discrete time or space signals and images, we're all very familiar with. We live in a digital age. And so everything we can represent as pixels, okay? And so basically for every pixel in your computer or your iPhone or your iPad, it has some value to it, okay? So typically when we have a function that's discrete, we use brackets to denote it. So S bracket n would be a one-dimensional signal, S bracket mn be for two-dimensional. So basically and the m and n are integer values. So basically we're saying that we can describe our image by indexing through integer values. So whenever you see S bracket something and what looks like integers, you know you're dealing with a discrete signal. Continuous time or space is typically what we use to describe what we see in the real world. So for example, if we're trying to image someone's body, look at their hand, their brain, their foot. Although maybe at the quantum level, there is some discreteness to it, you know, for all intents and purposes, we're assuming it's continuous to us. And so for that, we will use parentheses. Okay, so S of t for something varying with time, S of x for something varying in space, or in one-dimensional, or for two dimensions, which we'll deal with a lot in this course, this would be an image, S, which is a function of x and y, which is varying as a function of both x and y. All right. So we're going to start off with discrete time signal expansions first. And the purpose of the next set of slides is to say that how can we take any image or any signal and represent it as a sum of shifted and weighted delta functions. And so that's a very important concept. And so we want to sort of see how we do that. So we're going to start off with what's called the Kronecker delta function, which is a much simpler delta function to deal with. And the definition is shown here. It's very simple. It's delta of n is equal to 1 when n equals 0 and 0 otherwise. So this here is a picture of the Kronecker delta function. Now, another very important thing that we're going to do with delta functions is we're going to shift them. So notice if I took delta of n minus 2, that represents a delta function that's shifted over by 2. All right? So you want to get a little comfortable with if I have some function delta and there's an n minus 2, that will shift it one way. If it was delta of n plus 2, then it would shift it the other way. So if this was 0, minus 1, minus 2, then that would be my Kronecker delta function. So if it's been a while since you've dealt with mathy things, then that's one thing to sort of make sure you understand. Here's a two-dimensional Kronecker delta function. So delta of mn equals 1 when m equals 0 and n equals 0, and it's 0 otherwise. So this here is a picture of the two-dimensional Kronecker delta function. And let's take a look at some shifted versions. So in 2D, obviously, we can shift both along the horizontal and the vertical axes. And so it's useful to sort of see how we use mathematical notation to describe that. So this here is delta of m minus 2 comma n. So we've shifted 2 units along the horizontal axis because we have that m minus 2. Here we've shifted 2 units along the vertical axis because we have the n minus 2. And in this case, we've shifted 2 horizontally and 2 vertically because we have m minus 2, n minus 2. All right. So fairly straightforward, but it's useful just to sort of get a sense of what, these basic mathematical operations are. You're just shifting your object around in space. Okay, so that brings us to what we're going to call discrete signal expansion. And so the claim is, given any function g of n in 1D, I can write it as the sum, and notice these are Kronecker delta functions that are shifted in space along the axis, and then these are the weights. Okay, so let's look at an example of that. So let's say this is my function g of n, and this is the 0, 1, 2 coordinates. Okay, and this has a value of 1, this has a value of -1, and this has a value of 1.5. Okay, so it's not too hard to see that you could write this as the sum of these components, right? We have something that's delta of n, which gives us the 1 at 0. We have minus delta of n minus 1, which gives us the -1 at 1. And we have 1.5 times delta n minus 2, which gives us the 1.5 at the 2 location. So this is, if you understand this picture, that's really all the intuition you really need to understand what we mean. Now, of course, we can do this in 2D. So we could have any 2D function can be represented now as the sum of the shifted 2D Kronecker functions, each with some weight to it. So this is just showing for any 2D signal, you can clearly break it up into the sum of 4. In this case, this is a 2x2 image with values of A, B, C, and D, and it's not too hard to see that you can write it as the sum of these 4 independent or separate images. Okay. And so that's basically the image decomposition 2D. Each of these, is a 2-dimensional Kronecker delta function with some arguments. It's each of these has a weight. And obviously, if I took this and multiplied by A, I would get this would become an A here. So I would get this A. B times 1, I get that B. C times 1, I get that C. D times 1, I get this D. Okay. So this is just writing it out sort of in brute force, where I have my function g of mn. So this is my function, right, my image. So you notice there's an A times delta mn. So if I'm denoting this as sort of the 0, 0 coordinate, that's the delta at 0, 0. I have B times delta m n minus 1, okay? So that actually, in this case, looks like to be a mistake because this has it shifted over by 1 this way. So this actually should be m minus 1 comma n. Okay. I have the C that's shifted up 1 this way. So this is actually also incorrect. This should be m n minus 1. And this is D, which is shifted both ways. So it's shifted like that. So that's m minus 1, n minus 1. So that looks okay. Right. So basically, at the end of the day, we have all these shifted delta functions, each multiplied by the value. Okay, so let's go ahead and work out this exercise a little bit. So let's actually call this m and n for now. Okay. So let's say g of n. We're not going to do the whole thing, but just write it out enough that it makes sense. So g of mn So there's 7 at the origin, so we can write it 7 times delta of m comma n. Okay, because that's the Kronecker at the origin, plus 8 times it's shifted over by 1 along the m-axis. Okay, so we've done 7 and 8. Let's do number 1, plus 1 times delta. Now this is shifted this way, so we went 1 this way and then 1 this way. So that's going to be m plus 1, n plus 1. And you can sort of go on and sort of fill out the whole thing, but it's important to note that the sign here tells you whether you shift to the left or to the right or up or down. Okay, so if you're not comfortable with that or have more questions, just type it into the chat or let me know. Okay, so are there any questions on Kronecker delta functions? So Kronecker delta functions are what we use when we're talking about discrete time signals or images. Okay. Okay, a few slides back, I was a little confused about the discrete signal expansion. Okay, so I'm just gonna go back. Was it this? Can you tell me which slide it was? This one? Yeah, okay, great. So can you let me know what sort of was confusing about that?
When you're writing the numbers for like GN and then on the bottom right with the 1.5, I didn't quite follow. I think the scales of the dots, I'm not quite sure.
Sure, okay. So this is along the n axis, right? So we're indexing by n. So this is like n equals 0, n equals 1, n equals 2. Okay, so we're marching along. So these are just integers along this axis, 0, 1, and 2. And it's saying at 0, so g of 0 equals 1. Okay, so at this coordinate, I have a value of 1. Okay, so along this axis here, it's like 1, 1.5. And then at g of 1, I have a value of -1. So that's this one. And then at g of 2, I have a value of 1.5. So that's this.
I see. Okay, got it. Thank you.
Great. Okay, great question. Anything else before we move on?
I have. Sorry, go ahead.
Go ahead.
I was just gonna ask, like, because you're adding up all these values at different ends. How is it that they don't add up to like a big number, like a big value?
That's a great question. So the idea is, so let me try to explain that, and then we'll get to the next question. So so for example, the way it works is because delta of n. Let's look at delta of n. Okay, it's only got a value at one location and 0 everywhere else, right?
Yeah.
So basically, it doesn't contribute. So it only has an effect at 0, right?
Mm-hmm.
And then the next one is minus delta of n minus 1. And it's only -1 at 1, and it's 0 everywhere else. So the idea is delta functions don't interfere with themselves, with each other. So if I have a delta function here and another delta function here, I add them up and they don't interfere with themselves because they're 0 everywhere else.
Oh, okay, I see. Okay, thank you.
Sure, that's a really important concept to have. So I'm glad you asked that question. Great. There was another question.
Yeah, Professor. So why are we writing like the G function like this? What's the intuition behind it?
Oh, right. So it'll become a little more clear, but just to give you sort of a preview of coming attractions, the reason we're writing it this way is in general, in engineering science, it's always good to break down signals into smaller parts. Later on, when we talk about Fourier transform, we'll break them into sines and cosines. Now we're breaking them into, and whether it's delta functions or cosines and sines, it's what's called basis functions. And so the reason we're going to write them this way is because we know that it's fairly, if we can characterize the response of a system to just one delta function, right? Then we're going to say that then if I have this signal expansion, then I can predict the response to any signal. So the idea is for any arbitrary signal, we can express it as a sum of shifted delta functions. And then if I know the response, h, let's say h of n to the impulse responses, then by just adding up those responses, I'll be able to get the response to the entire input.
Okay, I see. Thank you.
So yeah, so maybe if you still have questions after we've gone up through convolution, then let me know. But we're sort of building up the ideas very slowly, but it's good that you guys are asking questions as we go along, because at the end, we're taking little steps, but at the end we're going to come up with something quite powerful. Okay, so we've gone over discrete time, which is, or discrete signal expansions, which is a little more easier to understand. Everything is integers. And so and anytime you get confused, it's good to go back to this discrete time and sort of make sure you understand this. Continuous time, we're going to go over, but the actual mathematics, if you really delve into it, is a little more complicated. So we're just going to give you the intuition, and we're not going to be real sticklers from a mathematical point of view. Okay. So the main thing is now, instead of a Kronecker delta function, we have what's called a Dirac delta function. All right. And this has a very funny definition. If you haven't seen it before, it's sort of interesting. It's defined as delta of x equals 0 when x is not equal to 0. And yet the area of this function is 1. Okay, so it's not defined anywhere except for at 0, which, as you know, 0 has infinitesimal width, and yet it has an area of 1. Okay, so the actual mathematics, sort of how you justify that is a little bit beyond this course, but we can give you some intuition. So imagine in class, Professor McVeigh introduced you to the rect function, okay, which we can also write as rect of x, like that. Okay, so rect of x, or this symbol of x. And so it turns out that if I have rect of x over any value L, that's just, so remember, rect of x is just a function minus a half to half and has a value of 1. So that's rect of x. Okay, so it always has width of 1, rect of x. And then the other important thing to remember for this class, if I take rect of x over L, that's going to go from minus L over 2 to L over 2. The simplest way to remember it is it's always going to have width of L. Okay, so rect x over any L is just going to give you a rect function of length L. So that's really useful to remember, because as you're doing problems, it's sometimes going to be confusing. Well, what is rect of x over W or whatever? Just remember then that's just the width of the rect function. In this case, we're taking rect functions, and notice that this has area. What's the area of the rect function here? Anybody? It's minus 1. Yeah, it's the area of 1. So to give this if I want to make this rect area of 1, what do I need to multiply it by to get me an area of 1? What should this amplitude be?
1 over L.
1.
Right, 1 over L. So actually we want 1 over L rect x over L. That would be a function that has width L and area 1. Okay. So in this case, what we're looking at is this. In this case, we're making L go to 0. So then the limit as L goes to 0, I'm shrinking the width of the rect function, but to keep the area equal, I've got to make 1 over L bigger and bigger. So you can think of the Dirac delta function as the limit of this function as L goes to 0. Okay. So that's sort of the intuition. It's just a very, very narrow object to represent an impulse. Okay.
I have a question.
Yes, go ahead.
So then when we refer to the delta function, are we referring to the Dirac delta function or the Kronecker delta function?
That's also a great question. So Dirac is when we're in continuous. Okay, so if we're talking about continuous objects, then we use a Dirac delta function, because we assume that it's like the difference between integration. So like, in continuous time, we're going to have to integrate, right? Yes. And then the Kronecker delta function is, let me write it here. Kronecker would be for discrete. And that's sort of, in math, that's where you see summations, right? So it's like the difference between whether you sum things up or whether you integrate them.
Okay.
Okay.
Thank you.
That's a good question. Anything else? So in 2D, we could have a 2D Dirac delta function, which is just delta of x, y equals 0, when x squared plus y squared is not equal to 0, and otherwise the area under the function is equal to 1. So the intuition is the same. You can imagine these little cubes that have area of 1, or in this case, volume of 1, right? And then as you shrink the base, they get taller, so they keep that same volume. Okay. The intuition is the same. We just want a function that gets very, very narrow, but has area of 1. All right. A useful fact for the future is the two-dimensional delta function is just the product of two one-dimensional delta functions. All right. Okay, so this is just a comment. You don't really need to know too much about this, but they are not ordinary functions. They're instead what are called generalized functions, defined by what they do in the integral. For this class, the most important property that you'll just want to know is what's called the sifting property. Okay, and that means if I have some function g of x, right, and I multiply it by a shifted Dirac delta function delta x minus x0, and then I integrate that product, what that operation does is it returns the value of my function at that point in space. Okay. So you can imagine, this is, the limiting case. Let's look at the case where, we can't really think about delta functions because they don't have any width to them, but we can sort of imagine an approximation of delta function is this rect function here that has area of 1. So you can imagine if I took this rect function and multiply it by g of x, then I would integrate, the area would just be this value here, right? And it turns out that if I do that, that area would give me g of x naught. So Dirac delta functions are really useful for mathematically saying, hey, I just want to pick out the value of a function at some point in time. So the Dirac delta function is a way of saying, okay, well, the way you do that mathematically is you take your object, multiply it by a Dirac delta function with x minus x naught to indicate where you want it, and then integrate, and that's mathematically what we mean by picking out a point in space. Okay. Some useful facts is the Dirac delta function has weird properties. For example, you have delta of a of x equals 1 over a delta of x. Just a useful fact. If we need to use that, we'll remind you a bit later. But it's just that Dirac delta functions can have some interesting behaviors. But what I want to really focus on is how do we represent a 1D signal, and in this case, is a continuous function. Okay. So we saw in the case of a discrete function, it was pretty simple. In discrete, remember for discrete, we were able just to represent it as a sum of Kronecker delta functions with different shifts and different weights. For a continuous signal, we have to replace a summation with an integral sign. Okay. We still have these shifted delta functions. They still have weights to them. But now we also have to add this sort of desire, this little increment. Okay. So that's because we're going from summation to integration. That's the other thing. But the intuition is the same. I mean, if we make let's say this is some delta x we have, we can approximate this as this, right? We can say, well, in the limit, if I have small enough delta x, then the integration just looks like representing the signal as a bunch of these shifted and weighted little tiny pieces, okay? So there's little, so you can think of them as that's how we're representing our signal as basically, remember in calculus when you sort of did an approximation of functions, now we're just writing mathematically that each of these, the components is a g of xi delta x minus I, okay? And then we're just weighting, and so each of these is a weighted and shifted delta function. Okay, and since delta functions don't interfere, we can just sum them up to create our signal. Okay, so we take the intuition from discrete, and then we just say, well, okay, in the limit, that should also apply for continuous time. Similarly, we can do in 2D, we replace the summations with two integrands. We still have our shifted delta functions with their weights. We add these I, d eta, and the intuition is the same. This can be approximated as the summation where these delta x's and delta y's are going to 0. Okay, and so basically any 2D function like this, you could just represent it as sort of the summation of all these little delta functions. So that's the basic intuition that we want to get across, which is that any function, 1D, 2D, ND, can be written as a summation of weighted and shifted delta functions. In discrete coordinates, then it would be a Kronecker delta function, and it would be a summation. And if you're dealing with continuous objects, it would be Dirac delta functions, and you're dealing with integration. Okay, so does the shift manifest itself visually on the GX graph? Okay, are you referring to this plot here? Yeah, okay. So I'm not sure I understand your question. Can you, you mean, so you want me maybe explain this bottom graph, right? Okay, so yeah, so let's say this is g of x, and this axis is x, right? And let's say that this was 0, this was delta x, this was 2 delta x, and this was 3 delta x. Okay, so we're going by increments of delta x along that axis. Then what we could say is this function here, right? You could represent it, and I'm just going to use delta function, but we could just say it would be like g of delta x, or sorry, it's at 0. So it'd be g of 0 times delta of 0. Okay, and this next one here, assuming it was in the limit, you know, it would be g of delta x times delta x minus delta x, right? Because that when you're dealing with Dirac delta functions, that minus thing is really important because it tells you where that Dirac delta function is located. Okay, and similarly, if we take this one, it would be g of 2 delta x times delta x minus 2 delta x. Okay, does that help explain it? Okay, great. So, so if everyone's okay with that, so what we've done now is we've covered signal expansions, and the idea is the course is not really about signal expansions, but having this background knowledge is going to be very useful because when we talk about Fourier transforms, that's actually going to be a different type of signal expansion. And then later on, you know, hopefully at the end of the course, we might even get into sort of modern medical imaging, which involves a lot of deep learning, and that's yet another sort of expansion. So the idea is we're always trying to break things down into building blocks, because if we can know how a system reacts to smaller building blocks, then we can understand the response of more complicated objects just by adding up the responses of simple objects. Okay, so that's the sort of philosophy behind what we're doing. Okay, so what I want to represent now is we want to represent, start introducing sort of the more formal way of talking about impulse responses. Okay, so formally what we would say is if I have some impulse response here, okay, so it has some input coordinate x1 and it's minus xi, so it would be represented as along the x1 coordinate, it would be a Dirac delta function located at xi. Okay, and it's saying, so that I'm saying that's my input, and then I have some function, I have some system L, so the L represents the system. Okay, and that's typically, mathematically, we call that an operator. It's taking one function and giving out another function. So that's like a super duper function. But L represents our system. And the reason we give it L is because we're going to really focus on linear systems. And so L is a nice term to use. But in general, a system doesn't have to be linear. But for this class, we will hope that we have linear systems. So all it says is, I'm going to write my impulse response as a function of two things. One is xi, which is the location of my original input was at xi, and then x of 2 is my output coordinate. Okay, and why is that? Well, let's do 2D first, and then that'll help explain it. So let's look at the 2D impulse response function. So this is delta of x1, oops, sorry about that, x1 minus xi, y1 minus eta. So this, in this coordinate system, I've got my x1 coordinate system and my y1 coordinate system. And the impulse is at the coordinates xi and eta because I have delta of x1 minus xi, y1 minus eta. Okay, so imagine I have a an object somewhere here in space that has some coordinate system. So that might be like my body. I could have a coordinate system for my body, right? Which is like x1, y1 would be the coordinate system for my body. I put myself into an X-ray machine, right? The X-ray film is behind me, probably. That film is going to have its own coordinate system, x2 and y2, right? Because it's at a different place in space. And so it's not necessarily going to have the same coordinate system. So then the impulse response is a function of where I am in that X-ray film space, for example, okay, somewhere in x2 and y2. And it's also going to depend on where the object was in my input space. Okay, so it's going to turn out in general, where an object is. So for example, if I move my object here, I might get some other response here, okay, which would be sort of a pain to deal with, but it's possible. So the idea is a system doesn't always have the same response to where things are in the input plane. In fact, probably the most important example of that, or one of the more important examples, is something that all of you have right now, where the impulse response actually varies depending on where the object is in space. So let me just throw that out as a question. Can anyone think about what object, what imaging system, and let's call it's a biological imaging system to use every day, you're using it right now, where the impulse response has a big dependence on where things are in the input space. Any ideas? Okay, yes, that's right, your eyes, right? So your eyes, if something is right in the center, very good focus. If it's out here, well, if you put it out here, then the response of the system is much worse. So that's why our brains are set up to always follow objects to keep them right where our focus is good. Okay, obviously peripheral vision is very useful, but the response of the system to something out here is not as good as it is to something here. So you can just, even if it's sort of in this plane, the focus won't be as good, right? Now, you don't always notice that because your eyes will track, but if you don't let your eyes track and just look forward, you will notice that the impulse response does vary depending on the input coordinates, okay? So that's what we would call a shift invariant system. And then in this course, we're hoping that mostly we have is shift invariant systems. Okay, so now we're going to spend the next couple of slides talking about linearity. So we're going to assume that systems in this class are linear, because if things are linear, as will the things, life is just much easier and we can do lots of problems. So there's two properties of linearity. The first is the addition property. And what that means is this. If the system is linear, let's call the system in this case is R, and I put some input I1 and I get some output K1, then that's sort of one set of inputs and outputs. And then I could also consider putting in some input I2 and getting an output K2, right? Now, if the system satisfies the linearity property, then let's say I come along with an input that's I1 plus I2. Okay, so I've added up the inputs. If the system is linear, I should be able to predict the output by just summing up the original outputs K1 and K2. So that's linearity. The other property that's very important is scaling. Okay, so once again, I have I1 going into my system R, and I'm coming out with K1. Okay, and in this case, you can sort of see the system sort of just rotates my object. Okay. Now, if I come through with I multiply my image by A1, let's say I increase the brightness of my image, then if the system satisfies scaling, then my output should also be scaled by A1, which means however much my input brightened, my output would brighten by the same amount. So that would satisfy scaling property. All right. So a system is linear if it satisfies both of those properties, okay? So it has to satisfy the addition property and also has to satisfy the scaling property. Okay, so it means if I have some input A1, I1 plus A2, I2, the output is just A1, K1 plus A2, K2. So that's all it is. That's a linear system. You've probably seen this before in linear algebra or other courses. So we're just gonna, this is for some of you, this may be a review. So let's actually do this now. So we're going to use the polling feature here. So we're going to give this a try. So I'm going to launch the poll. And your job is to tell me, and this is just, there's not graded or anything, but just tell me, you know, whether you think it's a linear system or not. Oops, sorry about that. So we're looking at A. Okay, so I think we're waiting for a couple more. So if you could just, so maybe one more person. Okay, great. So we have 10 yes and 2 no. Okay, so we're going to end that poll. Okay, so actually, let me try this. Can you guys see the results? Yeah, so that's the results there. And so let's take a look at it. So obviously, if this was democracy, then this would be a linear system. But it actually turns out this is not a linear system. So let's actually look and see why it may not be a linear system. Okay, so and this is, I think in homework 2, you may have some linear systems problems. That's been posted already. So I don't remember what Professor McVeigh assigned specifically, but I believe there might be some problems like this. So let's look at this. So we know that G goes to G plus 10, right? That's what the linear system is. That's what it's saying, right? If I put in G, I'm going to get G plus 10, right? So if I put in H, I'm going to get H plus 10, right? Okay. What happens if I put in G plus H? What does the formula say I should get out? And you can go ahead and type in your response if you want to. So if I follow that formula, I put in G plus H, what will I get out of this system? Okay, so one possibility is G plus H plus 20, right? That's what we think we should get, but look at what it's saying. It's saying whatever I put in, add 10 to it, and that's what you're going to get out. So if I put in G plus H, I'm going to get out G plus H plus 10. Okay. But if it was a linear system, you know, I should have gotten out the sum of those two outputs, which is G plus H plus 20. So these two things are not equal, so therefore it's not a linear system. Okay. Does everyone see that? Okay. So very simple example, and yet you can sort of see that it's a little tricky. So my general comment is, well, there's no quizzes in this course, so that's good. But if on a homework, the best way to satisfy what is a linear system is just go through the definitions and do something like this. Okay. So that's that one. Let's move on to B. Let me open up the poll for that. Let's get to there. Sorry, things are being a little slow here. Okay, so the poll for this one should be open. So same thing, is this a linear system or not? Okay, let me just share the results. So we have 75% yes, 25% no. So let's take a look at this and see what we think it should be. Okay, so we have, if I put in G, I get out 10G. If I put in H, I would get 10H, right? If I put in G plus H, I should get out 10G plus H, which is equal to 10G plus 10H. So it satisfies addition, right? Okay. If I put in, let's say, a scaled version of G, 2G, I would get out 20G, which is equal to 2 times 10G. So it also satisfies scaling. So we're okay on both counts. So in this case, yes would be the correct answer. All right. Everyone okay with that? Okay, last one is going to be this one, C. So this is a little more applicable to imaging, right? Where you do a lot of things where you can imagine moving an image. We do that all day, right? You're moving your mouse around. And so the question is that, when you do that, is that a linear system? Okay, waiting for one more response. Okay, great. So let's look at this. So this is also 75% yes, 25% no. So let's actually take a look at this. Let me, okay, so so we know that, you know, if G was this image, H, the output is just a shifted version of that, right? So similarly, let's say I had, you know, some other object. So I'm just going to map out where that was. That was there, okay? So let's say I had another object, which was here. Okay. So we know that the original object got shifted up 1 and over by 1. Okay, so this, I guess this was, let's see. What's the width of that object? Then it got moved over by a half. So this must be width 2, right? Got shifted up by half. And so let's say that there was some other object here. So that this, so moving this up, this is sort of 2, and let's say this is also 2, okay? So this has its origin at 0, and this has its origin, the x-axis has its origin, must be at 1, right? Let's move to over there. So this has its, this axis is at 2, right? So we imagine moving this object over, this would be at 3, right? The middle of that would be at 3. Okay. And then also we've moved them both up by a half. And so now their centers are at 1 here. Okay. So basically, if I have 2 objects and they both shift the same amount, whether I had each object in separately or together, they would still shift by that amount. So it satisfies additivity. Or if I even had them on top of each other, they still shift by that. They both shift by that same amount. So the system would satisfy additivity, okay? And then the scaling is, if I have my object, and let's say my object is this big, and I shift it, and now I made my object twice as big and I shift it, then it's just that object shifted multiplied by 2. So this would satisfy both addition and scaling. So it is a linear system, right? So that's good because we do this all the time in imaging. We move things around in space. And so if that was not linear, that would be a big problem, okay? Can you go over B one more time? This one, right? Okay. So was there a specific question about B? Was it the additivity or the scaling that was more confusing?
Just both, actually.
Okay, sure. So, so the way you go about these problems is you say, okay, if I have an input G, the rule, the diagram tells me just multiply by 10. Whatever's in the input, multiply it by 10, okay? So you want to think of things as black boxes, like I have some input, I don't really know what it is. And it just says, take my input, multiply by 10, and you get some output. Okay, so you want to think of things a little bit generally. So if G is the input, then 10 times the input is just 10G. If H is the input, then 10 times the input is just 10H, right? If G plus H is the input, then 10 times that input is just, 10 times G plus H, okay? But I can write 10G plus H, apply distribution, say that's just 10G plus 10H. And 10G plus 10H is just equal to the sum of my outputs to the original inputs. Okay, so the fact that this equals that's equal, that means additivity is satisfied.
Okay, why is it that when you put in 10, it gives you 10 times G? Or
when I put in G, I get 10G, right?
Yeah.
Is that?
Oh, but 10 is just showing that you're multiplying it by 10. That's all it is. It's not the.
Yes, that's right. So this means you're multiplying the two things together. So this is a multiplication operator, right?
I see. Okay. Yeah, I was confused about the 10. I thought it was an input. Okay, I see.
Right. No, this is part of the system. So you imagine drawing the system looks like that.
I see.
And also this system looks like that, right? So the system is sort of the thing. Yeah, good. Okay.
Yeah.
Okay, so let's go over superposition. And we're not going to go through all the hairy algebra, just want to get the point across so you have the sense of what we're doing. So just remember, we said that any function g of m, and we'll do it in 1D, can be written as a sum of, these are shifted Kronecker delta functions, each with a weight, okay? And I can imagine coming up with an impulse response, h of m prime k, which is the response to my system to a delta function located at k. Okay, remember, anytime I have something like delta m minus k, that means the delta function is located at k, right? And so just to sort of map out, I'm going to map out the first step, and then we're going to go to the next slide, which sort of shows it in more detail. But just as sort of how you'd go about that is, if this is a linear system, then I know that if I take, hold on just a minute. I want to figure, what I want to do is I want to say, well, what's the output? What's the response of my linear system to G of M? Right, that's what I want to figure out. Okay. So we're going to map out sort of our approach for doing that, and then we'll show the solution on the next slide. So I just say, well, that's just the response to this, right? Because I can write my signal expansion out like this. Okay. So the first thing I'm going to do is I'm going to apply additivity. Well, this is the response to lots of sums. And so by additivity, I should be able to write that as the summation of the responses to the individual components. Okay, and so on and so forth. And then, so that's applying additivity. And then because I can apply scaling, I can take this out and I can write it's just, this is a scaled input, scaled direct delta function. So that's just G of 0 times L of delta M plus G of 1 times L delta M minus 1, and so on and so forth. Okay. And then remember, this now is just an impulse response, H of M prime. In this case, the input coordinate is 0. Okay, and this similarly, this is the response to, there should be a minus 1 here, H M prime 1, because the Dirac is at 1. So you're seeing that the output to my any arbitrary input is just going to be a weighted sum of individual impulse responses multiplied by the weights. All right, so that's the general idea, and that's why we wrote the signal as an expansion, because since things are linear, we can break up things, addition and multiplication, we can sort of break out those effects. Okay, and that's just written in much nicer form here, so you can follow along here. Here we applied the addition property, right? Here we applied the scaling property. Here we apply the definition of impulse response. And here we're just writing it as a nice summation. Okay, so you can sort of see here, you have these different impulse responses, and they're each weighted by the weights. Remember, the weights were the weights of the original signal. Okay, so this is telling us that if we just knew these impulse responses, then no matter what the G of K is, so when you change the G of K, you're changing the input signal. So this just says, well, you don't have to you can, for any G of K, any set of numbers that gives me a G of K, I can always tell you what the output will be using this formula. So this is the property of superposition, and superposition means, when you gives you the response of a linear system. Okay. You can also do this in 2D and with integrals, and essentially you get the same thing. It's now, instead of we have Dirac delta functions and we have integrands, but you still see there's these impulse responses and their weights. Okay, so that's the idea. The same idea applies. Okay, so the next concept we want to introduce into getting to shift invariance or space invariance is the idea that if I have, in the top row here, I have my input object located at some point, and this is its response. So the idea is if I move my object to some other location in input space, if the system is shift invariant or space invariant, then my output should just look like my original output, but should shift it in space by exactly the same amount. Okay, so we already talked about one system that's not shift invariant, and which is the your eye, where if my object is here and I move it here, the response is very different. So that's a different system. But what we're going to be doing in this class is assuming shift invariance, and so we want to look at the consequences of shift invariance. And it turns out the intuition is very simple. If I have a shift invariant symbol, it's linear. If it's linear and shift invariant, I have very nice properties, which is that, let's say this is my input. So it's got values at 0, 1, and 2. Let's say this is height 1, maybe this has height 2, this has height 1. Okay, and this is its impulse response. So that's the impulse response, remember, is the response to that input there. So we know that this input will give us that output. Okay. Now, if it's shift invariant and linear, then we know that that second input is going to give us that output, which is basically, we use scaling. We scale the input by 2, so the output's scaled by 2. And we use shift invariance because the shape of it doesn't depend on where the input was. And then the next input is the same size as the first input, so it's got the same amplitude. and it's got the same shape because it's shift invariant. So we just shifted it over by 2. Okay. And so the output, if we were to draw the output, then would be sort of this overall sum of all those. Because if it's a linear system, we know that the output is just the sum of the outputs to the individual inputs. All right. So this is what we want to, this is the intuition we want to have for linear shift invariant systems. And the idea is this, what we've just described, if this was the input G, and this was the output, the impulse response H, then we're saying my output Y is just G convolved with H. So that picture we have mathematically, we're going to see is represented by convolution. Okay. Okay, and so let me just skip over that slide, just to give you a sense of what convolution is. Remember, we can, it's almost the same as we did for superposition. We're just going to change something at the very end, which is basically, well, first of all, let me go over the, I forgot to go over this. So, okay. So a linear shift invariant system is defined as follows mathematically. If I have my impulse response depends on the input coordinate xi and eta and the output coordinates x2 and y2, then if it's shift invariant, we're allowed to make this equality, which is, it's basically just based on the difference between my output and input coordinates. And if that's true, then that's the shift invariance. Okay, so the idea is, if a classic example is if I ring a bell today and wait 5 seconds and measure the response 5 seconds later. Okay, so the distance between my input and my measurement coordinate and my output coordinate in that case is 5 seconds. I've waited 5 seconds to see what my output was. Okay, then if I come back tomorrow and do the same thing and wait that amount of time, wait 5 seconds, then I should get exactly the same value if it's a shift invariant system. So it's only the output only depends on the difference between the input and the output coordinates, right? So that's going to be useful when we come to here. So once again, we've described our input as a sum of weighted, so these are the weights, G0, G1, G2, and shifted delta functions. Okay. And now we want to know, and we're saying that my impulse response now can be written as a function of the input, of the output minus the input coordinates. Okay, so it's no longer this m prime k, it's now m prime minus k. So we do the same thing we did before. Here we apply, going from here to here, we apply the addition property. Going from here to here, we apply the scaling property. And then going from here to here, we apply shift invariance. Okay, because we know that basically the response to delta of m is just h of m prime minus 0. Okay, and then the response to delta of m minus 1 is just response, it's just this response h of m but shifted by 1. Okay, and the response to this one is just the same response shifted by 2. So that's exactly the same thing we saw before, that as we move the delta functions, we're just, the shape of the response stays the same, but it's just shifted in space. So this would be h of m prime, this would be h of m prime minus 1, this would be h of m prime minus 2. And so if we do that, we end up with this very nice result that we can write it as this form, and this is what's known as the convolution sum.
Professor, can I ask a question?
Sure.
So what's the m prime here? What does the meaning of the m prime?
Yeah, m prime is just to say that it is, strictly speaking, it's in a different coordinate system. So that would be, for example, let's say, like if we go back to the X-ray example, my body is measured in m coordinates here, right? That's in one place in time. And then the X-ray film is somewhere else. So in that coordinate system, generally speaking, it's m prime. But in general, you know, we want things to be sort of, you know, assuming it's the same place. So if everything was fine, then we could also just say, well, if I could keep it in the same physical, if for example, the X-ray was the same width as my body, or everything, there was no magnification effects, then we could make the M prime and the M be the same. So for the rest of the course, we're sort of going to drop that. So don't get too hung up on it now, but just to be very rigorous and formal about it, it is M prime, because typically where you measure something is different from where the object is, right? Like when you look at a star, you're measuring a star that's up in space, right? But your telescope's down on Earth. So there's different coordinate systems. But then you can sort of take into account for that by saying, well, okay, well, then I know there's some magnification factor. So you can sort of take that out and sort of get to the same coordinate systems. So that's something that, that's what the M prime is.
Okay, so M is, so the H is M prime coordinate then, right?
Yeah. But
Okay,
generally what
okay.
we'll do is, in computers and things, we can always scale things up or down. So you can always make the M prime, scale it so it's equal to M.
Okay, I see. Thank you.
Yeah, I mean, it's sort of the same thing we do all the time, right? It's like when you look at a picture of someone, they look really small, right? But in your brain, you can imagine scaling them up to life size, right? So
yeah.
we sort of make that. So yeah, that's the. I'm just sort of giving you that so you can be rigorous, but don't get too hung up on that. Okay. Okay. So let's just spend the last part of this session on how you actually do convolution. We're gonna. I had some slides on Fourier theory, but we'll keep those for next time, because I think for today, just going over linear systems and convolution is probably sufficient. So this is really not a course about convolution, and we're not going to give you any very hairy convolutions, but it is useful to know a few basic things about how we actually do convolution, because this is sort of useful to have. So let's just go over a little bit of the definition. So this is the convolution integral. G of xi, h of x minus xi. Those are multiplied together, and then you integrate over, in this case, d xi. And the way we write this is g of x, and we typically use this sort of star asterisk symbol to represent convolution. Okay. So what does this mean? Well, it means that the formula is you take one function, g of xi, you take the other function, and notice it's x minus xi, so it means you have to flip it and shift it. So we'll talk about that in a minute. And then you multiply those two functions together, and then you integrate the product. And you have to do that over and over again. So then you have to repeat for each value of x. Okay. So if this was a course on linear systems, you'd be doing lots of examples of that. So since it's not a course on linear systems, we're not going to make you do very hairy examples. But I wanted to go over one extremely useful fact that you should know, which will be very useful in this course, which is this. If I take any function and I convolve it with a shifted Dirac delta function, it has the really cool property that it just shifts my function by that delta. Okay, so in this case, delta is this offset. Okay, so if I want to take an object and move it, the way I do it mathematically is I convolve it with a shifted Dirac delta function. And wherever the delta function is, that just moves my object to the delta function, the center of the delta function, okay? So we'll see that in a few examples. So this is the first example. So I have my function here, rect of x. And so mathematically what I'm doing is I'm taking rect of x and I'm convolving it with delta of x minus 1/4 plus delta x plus 3/4. Okay. And what does this do? This tells me that my output, so rect of x convolved with delta of x minus 1/4, is just going to shift the rect function so it's centered at 1/4. So mathematically, I write that as rect of x minus 1/4 plus rect of x plus 3/4. And that's my solution. Okay. Graphically, what it would mean is if I had my rect function here, it would be shifted, one would be shifted, so it would look like this, right? See, 1/4, half, So it'd go from 3/4 to -1/4, right? That would be a rect function centered around 1/4. And the other one is a rect function centered around -3/4. So it would go from -1/4 to -5/4. Okay. Sorry, things aren't really to scale there, but those are the two rect functions there. Okay. So that's really useful. So if this is probably one of the more useful facts to remember from this lecture is convolving with delta functions, shifted delta functions always just shifts your object. Let's see. Okay, so now let's do a slightly more complicated example, which is 1D convolution. So this is a rect function convolved with another rect function. Okay. I'm not sure you're gonna have any homeworks on this, but let's just go over it just for completeness because I think it is useful to know. So remember what we said is the formula is we take our g of xi. So g of xi is one of the rect functions. So that's just rect xi. And then h of x, h of xi was just also equal to rect function. Okay. And then what it's saying is I have to take that function and x minus xi is that function flipped around the xi-axis, right? Because so the way to think about this is evaluate at x equals 0, x equals 1, x equals 2. Okay, because remember I'm having all these things h of x minus xi. So when I plug in 0, I get h of 0 minus xi, which is just equal to h of minus xi. So in that case, I just, because it's symmetric, when I take the negative coordinates, it just flips, it looks the same. Okay. But let's look at another case. At x equals 1, I have to plug in, for x is 1, so I've got h of 1 minus xi. Okay. So the minus xi meant I flipped it, and then the 1 means that I had to shift it over. Okay. And so this is actually centered at units of 1. And it can get a little confusing when you think about, okay, you know, I have minus coordinates, I flip things over, I've added this thing, what does that mean? But you can always go back, and what's useful for, if you haven't dealt with images or signals too much, it's always useful to go back and say, okay, well, at least I know that it should be centered at 0, right? The center of this is going to be where this argument here, 1 minus xi is equal to 0, right? Because we know the rect function is centered at 0. So then I can say, well, I know that the center of the rect function is just going to be a xi of 1. Okay, so that's a useful little trick to play, because sometimes when you're dealing with images and signals, they can get a little confusing. Similarly, this is x equals 0.5. Okay, and so basically in this case, we have replaced x with 0.5, and this is going to be centered at 1/2. Okay. So that's the flipping and shifting part of it. So you can always sort of figure out that flipping and shifting. And then the next thing is we multiply these two things together. And so in this case, when we multiply the two together, I get a rect function. And then I would integrate over this multiplication. In this case, the area is equal to 1, right? In this case, when I multiply this function and this function together, there's no overlap. So the area is going to be 0. Okay. And in this case, when I multiply these two rect functions together, it only overlaps here. Okay, so that's the only area of overlap. And so in this case, the area is 0.5. So it turns out if I draw the output of the two things convolved, I end up with this very nice function. It goes from -1 to 1 and has a height of 1. So also it's known as the triangle function. Okay. So that's just a very simple example of what convolution is. And so when you hear people about flipping and shifting and multiplying, that's sort of how you would do that. Okay. And then for 2D, it's the same thing. We can write the 2D convolution integral, just replacing, now we have a double integral, and we have, sometimes we'll use 2 asterisks to denote 2D convolution, but if we're dealing with 2D functions anyways, then even if you write one asterisk, it's sort of understood that it's a 2D convolution. So you don't necessarily always have to write 2 asterisks. It's pretty obvious from the notation that it's like that. Okay. So let's go over some examples. In this case, we'll stick to a very simple example. So I have one function is delta x plus 1/2 y. So that's this guy here, right? It's located minus 1/2, comma 0. And the other one is a delta function, which is located 0, comma 0. Okay. And I'm convolving it with a 2-dimensional rect function, which is just this square here that goes from minus 1/2 to 1/2 on the x-axis and minus 1/2 to 1/2 on the y-axis. It's 1 within that region. So as Professor McVeigh was saying, it's a very useful function because we want to be able to, in imaging, we want to be able to crop. So like if you ever use, Photoshop or photos, whenever you crop something, if you have a square cropping, then that's just multiplying your image by a rect function. In this case, we're convolving this rect function with the sum of 2 delta functions. Okay, so because it's a linear system, convolution is a linear operation, we can imagine convolving each one separately and then adding the 2 things up. Okay, so if I convolve this rect function with the first delta function, delta xy, then that's just going to lead to it's going to be this delta function here. Okay, it's just going to be delta function that's not shifted. Okay, because that Dirac delta function is not shifted in space. Now, if I think about convolving it with the second Dirac delta, it is going to shift it. It's going to shift it by 1/2 this way, right? So that's going to end up being this delta function here, this rect function here, which is shifted over. Okay. So now I have these 2 shifted rect functions, and by linearity, I know I can add those 2 up to get my overall output. So the idea is this would have a value of 1 here. It would be 2 here where I add the 2 up, and it would have a value of 1 there. Okay. So this is a nice example because it emphasizes that when you convolve with a shifted Dirac delta function, it just moves your object to that location. And then if you have a bunch of these, then you can always do each one separately and then add them up at the end because it's a linear system. Okay.
I have a question.
Yeah, go ahead.
I was just gonna ask on the last slide. I noticed like that.
This one?
Yeah, this one. This one. Yeah. So I was just wondering when we're convolving like g of x with h of x, y, it doesn't have to be that the h of x is the one that's flipped and shifted. It could be g of x that's flipped and shifted, right?
Yes, that's right.
Okay.
So the flip and shift, yeah. Now, when you're thinking about convolving with Dirac delta functions, you don't really need to worry about the flipping and shifting because it's just if on one side you have Dirac delta, then you're convolving with something else. The Diracs just shift those things. So the nice thing about convolving with Dirac delta functions is we do it a lot, and you don't have to. It's an easy thing to think about. You're not thinking about flipping and shifting. It's just moving.
Oh, got it. Okay, thank you.
Okay. It's only when you have 2 objects that are sort of not Dirac, then you have to think about the flipping and shifting. But we'll sort of try to minimize that for this class because we don't want people to get too hung up on algebra. We want really to focus on the concepts. Okay.
Okay.
So I just have one more slide today, which is very similar to what you did for your homework 1. And let's just look at this from the point of view of what we just learned. So here's my object. Let's call it g of xy. Right? And here's my impulse response, h of xy. And this is my output g convolved with h. Okay. So, and then this is just going from the bottom to the top. You've just changed, let's call this h1. This would be another impulse response, h2, which obviously is got a bigger width, so it's going to blur things more. Okay. So one way you can think about this, obviously you can do it in MATLAB and not think about it and just get the output, which is what the slide was done with MATLAB. But it's also useful to go back and let's just sort of summarize sort of the key intuitions that we've learned from this session, which is that this object here, g of xy, if I blow it up, let's say I blow it up, right? I can imagine it's made up of lots of little tiny delta functions, right? It's the sum of all those little tiny delta functions, okay? And each one has that response, but each one has that response shifted, okay? So what it means is my output is just, it's going to have some blurry response here, and there's going to be a blurry response here. And so my output is the sum. If you can think of each of these points giving you a blurry response, then my output is just the sum of all those blurry responses. Okay, so that's really, that captures sort of a couple of things. One is shift invariance, because I said, and I don't care where that dot was in my input image, it's always going to have the same response. Okay, so that's shift invariance. The shape of that response doesn't vary. And so it satisfies shift invariance. And then the fact that I can add up those individual responses satisfies additivity. Right. So that's that's sort of a good thing to keep in mind in terms of why convolution is so useful and why shift invariance and these concepts are useful, is that it says that if I know my impulse response, then that is enough information to characterize my entire system. Okay, so that's really why we talk so much about impulse responses. And then for next week, and it's already been touched upon in the class lectures, is the next thing we're going to focus on is, we have h of x, and then next time we want to look at what's the Fourier transform of h of x. So if I put that in a Fourier transform, and we get some Fourier transform big H case of x, and this is what in class we call the modulation transfer function. Okay, and so it's going to be useful for us to look at things in both domains, because the way we understand signals and images, being able to go between one domain, image domain, and then the Fourier domain. Sometimes it's easier to do things in the image domain. Sometimes it's easier to do things in the Fourier domain. All right. So I think so. We'll save this part for next time, simply because we're sort of running short on time. So we'll end sort of the formal presentation here. We have a few more minutes. If anyone wants to ask any follow-up questions, we can certainly do that.
So, Professor, we need to have like a shift invariance as well as a linear system to use convolution. Is that right?
That's right. That's correct. Yes.
Okay. Thanks.
I have a clarifying question on the 2D convolution example. When you drew those squares and you wrote 1, 2, and 1, is that just, can you elaborate on that, or what are the units at the bottom?
Yeah, so that would be this blue color, let's say this blue color, everywhere there's blue color, that means that my function is just 1 everywhere in that blue square, right?
Mm-hmm. Oh, I see.
So then this is saying that everywhere it's blue here, it's 1. Everywhere it's green here, it's 2. Everywhere it's green here, it's 1.
I see, because when it's overlapped, you added the 1 plus the, I see.
Yeah. Okay. So that's a little bit, right. So the way we can represent 2D functions, that's a good question, is sometimes we just represent a 2D function as by their color or their intensity, right? Now, the other way, obviously, you can draw 2D functions is you could draw them like this, right? You could sort of show the height, right?
Mm-hmm.
So you could say that is height of 1. But then that gets a little, you have to be good at drawing and things like that, right? So, and obviously when we look at images, typically we're just looking at the brightness or the color.
I see. Okay, great. Thank you.
Sure.
So a follow-up question, so what's the value of the convolution of this? Is it 4?
Well, graphically, this is the solution, right? This picture is the solution. If I were to write it mathematically, G convolved with H would equal rect of XY, right? Because there's the convolution with delta doesn't shift it at all, plus rect of X plus a half comma Y. Okay, so that's just basically, so the first rect is this rect here. Okay, and the second rect is this other rect here.
Oh, okay, so we're adding up the area, basically.
Well, not the area. The rect function is basically, think of a function is just something that returns a number, right? So rect of xy just says if the absolute value of x and y, either one is less than a half, then I'm going to return 1, right? That's all. That's what the rect function means. So it's basically saying where they overlap, they're both returning 1. So when you add them together, the summation is returning 2, right?
Yeah.
Where they don't overlap, then they're just both returning 1. And so the output is either 1 where they don't overlap or 2 where they overlap.
Oh, okay. Okay, so so the convolution is a function. Okay, I see. I see.
Yes, that's an important thing. The convolution is really an operation. So it takes it takes 2 functions or 3 functions or whatever and returns another function. Just
Okay,
like any system, a system you could think of as an operator. You know, a function, as you know, takes in a number and gives you a number, right? An operator takes a function and gives you a function out. So it's a sort of like a super duper, you know, sort of the next level up from a function.
Okay, yeah, that makes sense. Thank you.
Sure.
So are these numbers somewhat arbitrary, like the choosing the value of 1? Because would it just be analogous to our homework problem where it's like we do this matrix of zeros and then where the cross was, it was 1s?
Well, in this case, because I define it as rect of xy, then the formal definition of rect is it's 1 in that square and it's 0 everywhere else.
I see.
Yeah.
Okay.
So it's just a really useful function to have because, you know, it's exactly because of that cropping function that, you know, if you imagine cropping an image, right, you want to keep it the same everywhere in the rect. So that's multiplying by 1. And then 0 is like getting rid of everything else.
Okay, got it. Thank you.
Sure.
I have a question about like the using the delta function, like for convolution.
Yes.
So when you're using the delta function, I mean, I understand that you are actually shifting like the delta function, but it's just because you're not, or not, sorry, I'm trying to understand how is it that like the idea that you talked about shifting, like how does it look when you actually, like how do you get this final like image from shifting if you were to shift and flip the delta function? Like I was just trying to understand how we get this. Yeah.
Right. I think so. So your question is, so I just let me try to rephrase your question to make sure I'm answering it correctly. So one thing is obviously we've just told you if you convolve anything with a delta function, it just shifts the other function, right? So is your question, how do you get that sort of fact from the fundamental definition? Is that your question?
Yeah. I'm trying to like connect it back to the fundamental definition.
Sure. Okay. So let's. I think what I can do is let me bring up something else. Notability. Let me draw. I'm going to draw this out because it'll be a little easier. Okay, so let's just do a really simple example then. Oops. Okay, so imagine I have, let's say, let's just say I had my object here, right? Whoops. I don't want it to be that complicated of an object. Notability has these new features that are nice, but I don't really know how to use them all yet. Okay, so let's call this g of x, right? And then let's have another one where we're going to have a delta function located, let's say this is 0 and it's located at 2. Okay, so we know what we've just said is that, and let's say this goes from, in this case, since that's 2, it's -2 to 2, let's say, to keep the units the same. So we know that, you know, if I were to convolve these two, right, then I would just get, this is delta of x -2, and then the convolution would just be g of x -2. So which would look like, this was 0, it would just shift it over like that, right?
Yeah.
Okay, so that's sort of, so that's the useful fact to remember. So even if you don't know how you get it. So now what we're going to do is we're going to go over, you know, how would you get this from the flipping and shifting property, right?
Yeah.
Okay, so there's 2 ways you can do it. One is you can sort of think about, well, you know, this is symmetric, right? So in this case, it's if I flip it, it doesn't, it's the same, right? Okay, so we can think about that. And then we know that from our example, as we added the different x's, you know, it made it move to the right. Okay, so let's look at that. So for example, if I were to shift it over, so this is g of x, but it's also equal to g of minus x, right? Those are the same, right?
Right. Yeah.
So imagine shifting this over to the right. Okay. So notice as I shift it over to the right, it's going to overlap with my delta function until I shift it over how much?
To after past the 2, I think, right?
Yeah, it's going to shift over till this back edge here no longer. So it's gonna stay. So basically, think about it this way: from 0 to 4. You know, here's the delta function, here's the rect function, right? And I start shifting. I start shifting it like this, right? And they start overlapping, and they keep the same overlap. And the delta function has area of 1, right? So so it sifts out. And remember that when I multiply by a delta function and integrate, it's the sifting property. So it just picks out the value of the rect function, which is 1. So the value stays at 1 until I shift it all the way here, in which case it no longer overlaps. So the value goes to 1. Whoops. Let's go back. So the value goes to 1 and stays at 1 until it shifts off, right? So it's like, and then it's 0. And similarly, if I go the other way, there's no overlap, so it's 0. So that's how, so it comes from the sifting property, which is the delta function. Whenever you multiply by a delta function, it just sort of picks out the value of the function at that location. And so it just picks out the values of the rect function until it no longer overlaps. And that just has the same consequence as just shifting the whole function over. So once, it's useful to do it once, but then once you've done it once, you go, okay, then I can just remember that that's what it does.
I see. Okay. Thank you.
Sure. Anything else? Okay, well, I think hopefully this was helpful to you. If you have suggestions on how to make the format better for the next session, the next session will be we'll be going over the Fourier transforms, and those will certainly be useful for CT and then incredibly useful for MRI. So let's see, anything before we end today?